So the last bit of theory material that you're going to need to know is um, is how to work some various derivatives when dealing with vector valued functions. We also want to touch on basic integration of vector valued function. We want to make sense of a few things, right? Like you recall from chapter 11 the idea of a dot product or the idea of a cross product, and you can recall that a dot product was of a vector times a vector was a scalar. The cross product of a vector and a vector was itself a vector. Now, we want to try to think about what this means when discussing vector valued functions. Particularly, the result of C is going to be interesting. But first, let's just start with the basics. So you're given some vector valued function, and you are asked to take the first and second derivative of that. So that's what we're going to do right now. We'll go through this quickly. So remember that when you're taking the derivative of a vector valued function, we are simply going to take the derivative of each component with respect to t. So what is that going to look like? It should look like this. So the derivative of cosine of t would be negative sine of t. All right, now don't forget your direction here. So it's easy to forget the I, the J, the K. So continuing, the derivative of sine of t is just cosine of t. And finally, the derivative of 2t with respect to t is just 2. All right. So now, just as you would assume, the second derivative, r double prime, would just mean that we're going to take the derivative of r prime. Right? It's quite simply in case no one, if your calculus teachers never made it apparent, to discuss if we think of r prime of t as the rate of change, that's an interesting question. But what is the rate of change of the rate of change is also an interesting question, right? If you tell me population is increasing, well, I can draw a couple different graphs. Is population increasing like this, or is population increasing like this? Right? The rate of change matters. So, but nevertheless, let's just get back. R double prime, so the derivative of negative sine of t would be negative cosine of t. And the derivative of cosine would be negative sine of t. The derivative of 2 is 0, so we won't write a 0k, but we can assume it's 0k. Okay, well, let me just slow down for a second and make sure that I have not made any silly mistakes. I know my wife doesn't believe that I ever make mistakes, but I tell her I do. That's a joke. You should have laughed. I don't know why you didn't laugh. Okay, ready? So let's actually look at part C. So a dot product. Interesting. Well, we're going to dot r prime with r double prime. So kind of bear with me for a second as I write this out. Actually, I tell you what, to kind of save space. So over parked off here, I have r prime and r double prime that we had produced from the previous page. And I'm going to go ahead and go component by component, setting it up the dot product. Okay? So you recall the dot product. It's just going to be, start with the I component. So this is going to be negative sine of t multiplied by negative cosine of t plus. All right, now we go to the j components. Are you thinking I forgot an I here? Well, you would be thinking incorrectly, right? Because remember, the dot products are the dot products of two vectors is a scalar. It's not a vector. So hold on. So now we go to this j component times this j component. So that would be cosine of t multiplied by negative sine of t. And finally, if I can squeeze everything here, it's going to be the k components, the product of the k components. So 2 and, well, there is no k component for r double prime, so it's 2 times 0. All right, well, let's go ahead and multiply this out. We end up with, well, negative and a negative is positive, so this is just sine t cosine of t. And then we have a negative and a positive, so that's going to be minus sine t cosine of t. Actually, I wrote cosine first, so I'll write it first here. Cosine t sine t. Now, if you were to combine these terms, you have a positive sine cosine and a negative sine cosine, so they are going to completely cancel, leaving us with just 0. But what's more interesting is, bear with me for just a second. For the dot products that we had encountered in chapter 11, right? If you took vector v dot vector u, you always ended up with a scalar constant, right? Now, what I need you to understand is that if you take the dot products, listen to me, please, listen, write this. If you take the dot products of vector valued functions, you are still going to get functions, but you're not going to get vectors. So, for all intents and purposes, we can think about this as a scalar once you know what the value of t is. So I'll say that one more time. The dot products of vector valued functions still produce functions, but they're real valued functions, right? Like, remember the types of functions you dealt with back in algebra, f of x. These are what we call real valued functions. So you'll still get functions from these dot products. Just you will not get vectors, valued functions. I hope that makes sense. So, and what is the last bit of information to do? Well, we have operated under the assumption that cross products of vectors yielded a vector, and indeed that still remains the same. All I'm going to do is I'm not going to go through the cross product here. I'll just set it up for you. So it'll take me a second to set everything up. Actually, I tell you what, let's make this a little bit easier. I'm not dodging doing cross products. Actually, I am. I lied to you. Slightly lazy on my part, but I really I want to go ahead and get to the material, the newer material that you have not had exposure to. At this stage, you know how to do a cross product. So, setting it up, I will. You can go on your own time. You can go through and compute the dot product, and you can see if you and I are getting the same result. So this is what I'm getting for part D. 2 sine of t I minus 2 cosine of t j plus k. All right. So assuming there's no silly mistakes, we've now done a few different derivatives. So where do we go from here? Well, I want to talk about a concept of what we call smoothness in mathematics. So like intuitively, if I were to say a curve, right? A curve is smooth. Like our intuition can fill in the gaps, right? Most students can kind of envision what a smooth curve would look like, right? A smooth curve. And most students can envision, a curve that's not smooth, right? If you had something like that, or, so some type of break, some type of abrupt change. But in mathematics, we can't be sloppy in our language, right? We need to formalize the language that we're using. So when we say smooth, that's a smooth curve. We need to define what we mean by smooth, and I try to blend formal and informal in my lectures. Sometimes it's for the good, sometimes it's for the it doesn't come out as well. But nevertheless, if you think that I'm either being too informal or too formal, you can always reach out to me, and I'll see if I can better explain. Nevertheless, ready? Let's discuss. So, a vector valued function is considered smooth on an open interval. Now, so in other words, the whole curve doesn't have to be smooth, right? Just on an interval, right? Maybe from here to here, that interval I would be smooth. So we would consider a vector valued function smooth on an open interval I when the following criteria is met. So first off, your derivatives f, g, and h have to be continuous. Now, we've discussed continuity in the previous videos. So your derivatives have to be continuous, and r prime of t cannot be equal to 0, the 0 vector. So formally, this is what criteria needs to be met in order to say that you have a smooth curve. But intuitively, when a curve is not smooth, what's going to happen is it's just going to make some abrupt changes at a point, right? So like you can see this abrupt change at a point. And what we call these points where these abrupt changes occur, we normally refer to them as cusps, or sometimes for my engineer people, nodes. Okay, so let's look at example 3. So you've already seen the curve, the graph, right, of example 3. I've reproduced it here, and if you don't mind, do me a favor. We're a little bit spoiled. Like with this question, we're slightly spoiled here because we already have everything beautifully mapped for us. But let's do this, right? Let's tackle the question the way it sits, because I'm not going to give you this this curve perfectly labeled on a test. So let's just tackle the question the way it sits, and then we can look at the geometry and make sure we are in the right. All right, so it asks us to find the intervals on which the following curve, represented by this vector valued function, is smooth. And we have some domain restrictions on t, so it's from 0 to 2 pi. And ready? Let's go ahead and get started. So recall on the conditions that needed to be met, right? The two conditions were f prime, g prime. Now this is in 2D, so we only need to look at f and g. Let me see if I can write that a little bit better. So recall that f prime, g prime are continuous. And r prime of t does not equal 0. Ready? So let's take our derivative. First things first, step 1. Let's take the derivative of r. So really quickly, the derivative of r would be negative 5 sine of t plus 5 sine of 5t I'm going to make sure I have enough space. All right, and that's now plus, taking the derivatives again, what would that be? 5 cosine of t minus 5 cosine of 5t. So hopefully that is not too small on your screen, but this is cosine of 5t, this is sine of 5t. Okay, well, let's take a look at, so let's just label. So this portion right here, this would be f prime. This portion right here, this would be g prime. And what we're going to do is we would have to confirm that f prime and g prime are continuous. Now, I've already practiced that skill in the previous video. So I will go ahead and state that they are continuous. So let's check that off. And now that second criteria, right? That r prime of t does not equal 0. Interesting. How do we tackle that? Because I have r prime of t. And basically it can't equal 0. And so what we want to do is we're just simply going to end up setting r prime equal to 0. But if you just get in the habit of plugging a 0 right here, you're going to miss, you run the chance of missing what we mean by r prime can't equal 0. So let me make sure you understand. That 0, what is a 0 vector? And a 0 vector would mean you have 0i plus 0j. So that's an important thing to keep in mind. Well, how are we gonna tackle this? So let me see if I can copy and paste this. Entertain yourself for a second. It's hard in the limited amount of space that I have. But then again, even when I'm in a classroom and I'm surrounded by whiteboards, I still never feel that I have enough space. So I don't know. Maybe I just need a classroom that's wall to wall, chalkboards and whiteboards. Okay, so that is our prime. We're gonna set that equal to the 0 vector. So 0i plus 0j. All right, so hopefully that comes out clear on your end. How does this work? Well, in essence, we're going to end up setting each component equal to 0. So I'm going to take this first this I component, and I'm going to set that equal to this I component. And then I would take this j component, and I would set that equal to this j component. So I am just setting the components equal to 0. Now, I'm only gonna, this is gonna take me just a second to unpack. I'm only gonna do the first part of this. So I'll go ahead and write it. So I'm gonna go ahead and take -5 sine of t plus 5 sine of 5t. And I want to set that equal to 0. All right. So setting this component equal to this component. Okay. So how are we going to do this, right? So let's think about that for just a second. What value of t would make this a true statement that it's equal to 0? Well, even if you're extremely savvy with doing mathematics in your head, that's still fairly hard to do. So what I'm going to do is I'm just going to go ahead and factor out a 5. So let me rewrite that. In fact, I'll just go ahead and factor out a -5. So let me make sure I'm not doing anything silly. So if I factor out a -5, I would just be left with sine of t, and now this would be minus sine of 5t. That makes things slightly less cluttered. Let me complete that last parenthesis. So now this is slightly less cluttered. Let you and I agree that this -5 here has no bearing on what value of t makes this equation equal 0, right? You can't, this is just a scalar. You're not going to worry about that. It's in here. If this equation equals 0, it's going to come from inside here. This is, again, a little bit too hard to do just in your head, at least in my head. And now you're going to start to see why you spent time in trigonometry studying things like identities. Because look, the reason why this is hard is because it's a sum. Or now, when I say I know we are subtracting, I get that, it's a difference. But what I mean, it's a sum or difference, if you like, not a product. We want to turn, when we're setting equations equal to 0, we're turning sums to products. Listen, stop daydreaming. Come back to me. The whole point of factoring, why you factored all through high school, was to turn things like this, sums, into products. that looked like this. And if you can turn it to a product, then it's very easy to use the zero product principle to figure out what makes it equal 0. So we don't have that here, right? So we need to be able to turn this into a product, and we can do that. There's some identities that are built for that. These are called sum to product identities. Now the one that we're going to use is, if I have enough space, it's going to be, if you have sine of, let's say, alpha minus sine of beta, right? And that is what we have. We have sine of alpha minus sine of beta. Well, we can turn that into a product, and what would that look like? It would look like this. 2 sine of alpha minus beta over 2 times cosine of alpha plus beta over 2. Now, if this is a little bit too if unreadable, you can look it up, the sum to product formulas on the internet, or your formula sheets if you like. Now, let's just apply this formula. So in this particular case, we're going to let alpha be t, that's the first angle, and we would let beta equal 5t. And that's it. So what's going to happen right now is I'm going to use this formula, this identity, and I'm going to plug in t and 5t. Bear with me. Let me write it. So that's going to give us 2 sine of, that's going to be t minus 5t over 2 cosine of t plus 5t over 2. And now, from here, the first thing I need to do is grab another blank piece of paper so that I have space. So hold on, let me see if I can find where I was at. Should be here. See if I can copy and paste that. All right, so what are you doing right now? What you're doing is just entertaining yourself. That's what you're doing. You have nothing to do right now except just entertain yourself. All right, and let's continue this game. Well, of course, we got some, I can combine the numerator t minus 5t, that's just negative 4t. I can combine this numerator, that's going to end up being 6t. So let me go ahead and write that. Since I'm only going to do one of these smooth problems, I'm taking my time. And now let's go ahead, and what's going to happen right now is I'm going to divide 2 into 6. I'm going to divide 2 into negative 4. And the other thing that's about to happen is I'm going to use the idea that the sine function, sine of negative x, is equal to negative sine of x. This is just a statement that, if you recall, there's some symmetry based on if it's an even function or an odd function, and sine is an odd function. It would be a shame if no one ever really explained to you why that is the case. I will restrain myself from explaining a very simple explanation, but I will have to restrain myself. So what we have is, right now we have one of the things I need to make sure I do not forget about is my negative 5. Remember that I had factored out, so I'll get back to that in just a second. But I have 2 sine of negative 2t cosine of 3t. All right, and that was, we still got it set equal to 0. Okay, so let's go ahead and use this this property of sine, that it's an odd function. So basically, sine of a negative x is just equal to sine of x, the opposite sign. So I'm going to rewrite this as sine of just 2t, not negative 2t. And I can do that as long as I'm willing to bring that negative out front, if you'd like to think of it like that. And let's go ahead and get to where we are. So here's my negative 5 from the previous page. I'll use a different color. That's still sitting out front. And now I have negative 2 sine of 2t cosine of 3t is equal to 0. Now we have something, right? Before I did this, it was really hard to figure out what value of t would make this, make this equation, the left side equal 0. But now that I have a product, if I can make this part equal 0, right? If I can make this factor equal 0, then it all becomes 0. If I can make this factor equal 0, it all becomes 0. So let's look at each factor one by one. So I'm going to look at this factor first. So negative 2 sine of 2t. My question is, what values of t would make this equation equal 0? Well, I don't have time to go back and teach you trigonometry. I mean, I can help you if you need help, but you'll have to I'll have to put that on your shoulders and let you come contact me. But it's fairly simple. Remember your interval. It's from 0 to 2 pi. So we only are interested in the t values from 0 to 2 pi. And all it is you just using the period of the sine curve. And we end up with the following. Let me figure out where I'm at here. So it should be t should equal, all right, my apologies. I said I wasn't going to teach you trigonometry, but I don't think I have my answer key anywhere near me, so I got to make sure I'm not making any silly mistakes. So sine of t, regular sine of t equals 0 when t is equal to 0, pi, and 2 pi. Now I don't have t, I have 2t. So I need to couple this with the fact that the period of the sine curve is 2 pi. So that means every 2 pi it's going to repeat itself. Okay, so now by the way, this is, you can if you know how to do this trig part, beautiful, you can kind of check out for a second, but I need to make sure I don't make any silly mistakes because I don't have an answer key in front of me for some reason. So, okay, I don't have sine of t, I have 2t. So I basically, what I want to do is take 2t, set that equal to 0 plus 2 pi n. I want to take 2t, set that equal to pi plus 2 pi n. And I want to take 2t and set that equal to 2 pi plus 2 pi n. And now if I just divide both sides by 2, then what I get is t is equal to pi n. Then I get t is equal to pi over 2 plus pi n. And then I get t is equal to pi plus pi n. Yeah. So, all right. So at this stage, now I think I should be able to figure out what values of t would work. So I'm going to take this, place that here. I'm going to take this, place that here. Take this, place that here. All right, so the game I'm about to play is I'm going to choose some values for n. And trying to organize this. Yeah, so I'm going to choose some values for n and plug them in. There we go. Okay, so now the aside is done. I'm sorry I had to set this up because, again, my apologies, I didn't have the answer in front of me. So what are we doing if maybe I've lost my audience, right? Well, that's okay. So what I'm going to do is I'm going to choose some values for n, and I'm going to be plugging those in, that value of n for each one of these. And the game is that as long as the result is between 0 and 2 pi, then that value of t works. As soon as I get to a value that's larger than 2 pi or less than 0, then I can stop playing the game. So if I were to choose 0 and plug it in, well, pi times 0 is 0. And then I would have pi over 2. And then I would have pi. Now, if I were to, the next value, 1, so let's see what else I get. So that would be pi, plugging in 1 for n, 3 pi over 2, and 2 pi. Now, I would choose n is equal to 2 next. Now, if you plugged 2 in for here, you would get 2 pi. But do you see how that as soon as I plug 2 in for this function, I get 2 pi plus pi over 2, which is larger. It's outside the interval. So if I plug into 2, I get 2 pi. But of course I already had 2 pi, so that's not adding anything, any more information. The rest of these, it's not going to work plugging 2 in for the other two functions. So at that stage, I know I'm done. So so here it is. I found everything that I needed, everything that I was looking for. So let me clear this. Let me clear some of my work, and now let's finally answer the question, because what I've done is I figured out what values of t would make this I component equal 0. Well, what are they? Well, here they are. These are the values of t that would make the I component equal 0. Now, I would have to do the same thing that I just did for cosine, only that the good news is if I believe, let's see here. Yeah, I would have to go through the exact same sum to product formulas that I did with cosine, and then I would have to figure out which angles do they have in common, right? So if you can imagine, if I did all of this for the I component, imagine if I had another little t-table for the j component. Well, anything over here would make I equal 0. But the question we had asked is, when is r prime of t equal to 0? So I would need to know which do they have in common, right? So that's really the question that I would be answering. And now let me just go ahead and get us to the result. So if you were to go ahead and do that exact same sum to product method for the j component, and then you were to figure out what they have in common, here's what they would have in common. When t is equal to 0, both of these components are equal to 0. When t is equal to t is equal to 0, or pi over 2, or pi, 3 pi over 2, and finally, or 2 pi. If you were to pick any of these angles, and you were to plug those angles in for your derivative, you would end up with 0i plus 0j. That's what we just spent the last 10 minutes plus doing. That is the violation, right? That's the second criteria. So what you can expect is that when t is equal to these, you should not have a smooth point. And now let's look at the picture. You can see it. Notice that at these points right here, this is exact when t is pi over 2, pi, 3 pi over 2, etc. This is exactly where you do not have, that's an abrupt change. This is not smooth at that point. But everywhere else is smooth. So we need to answer the question. Find the intervals where your function is smooth. Well, it's everywhere else except those angles. So we'll take a break after this, but it's smooth from what? From 0 to pi over 2, from pi over 2 to pi, from pi to 3 pi over 2, and from 3 pi over 2 to 2 pi. It's smooth on all of these intervals, but look, you need, just like in conversation, we use words like and. That's not the word and. Sorry, I'm trying to think. And, or we use phrases like that to join statements, right? We join our statements with phrases like that. We need to join these statements. This is a statement, this is a statement, this is a statement. You need to join them. And we would do that by using this notation U, and this means union. All right. Well, I'm going to venture to say you didn't like that problem, and that's okay. That's understandable. But you do need to find some practice with that problem. So you should jump in at some point in time to try to find some practice problems. We will conclude this video, and I will see you in the next video.